Hello, everyone. My name is Jing Liu, the Managing Director of the Michigan Institute for Data Science, or MIDAS. I would like to welcome you to today's workshop, and I will first say a few words about who we are. MIDAS is the central unit for data science at the University of Michigan, with more than 360 affiliate faculty members. Patrick, could you advance the slide? So about 1/3 do research that is related to biomedical sciences in some way. We also have a very strong student community. Our faculty's expertise lies in data science theory and methodology, and their applications in almost all research domains. Next slide, please. MIDAS plays a major role in 3 areas. For research, we develop guidance and resources for the data science community with a current focus on reproducible data science and ethical data science. We provide funding, training, and dataset access, and we facilitate new ideas and teams with a various number of programs. For education, we offer a postdoctoral training program and a graduate certificate program, and many opportunities for experiential learning. And we enable the translation of data science research into positive social change. Next slide, please. We don't do any of these alone. We have many campus and external partners. In 2020, we worked with more than 40 companies from many sectors, government, company, and nonprofit organizations. Today's workshop is intended to be educational for the general audience, but it's also a way to let MIDAS-Owkin scientists get to know each other and think about new research ideas. We're very glad that we can offer this workshop to a broad audience over Zoom, but I want to remind everyone of the challenges of Zoom events and ask that you be patient if we encounter any tech issues. Now I'll pass on to Patrick Sinchan, Partnership Manager at Owkin, and let him introduce his company and today's sessions. Patrick, please take over.
So thank you, Jing, and good morning, everyone. My name is Patrick. I'm a Partnership Manager at Owkin. And we are very excited today to host this workshop with MIDAS and are looking forward to some great scientific talks and future partnerships with the University of Michigan. Owkin is a French-American AI-driven life science biotech company, which was founded by our CEO, Dr. Thomas Clozel, and our CSO, Dr. Gilles Wainrib. And our offices are located in New York City, in France, in the UK, and Switzerland, with over 100 full-time employees. And since our founding in 2016, we have raised over 70 million of venture-backed funding. Our mission is to apply machine learning to develop novel predictive models to advance patient treatments. Our models can be applied for patient stratification to predict treatment response, survivorship, and biomarker discovery. And this is possible via a unique federated research ecosystem we have developed, in which you will hear more about in these talks today. At Owkin, we have developed these models using diverse data sets, including histology, radiology, clinical data, next-gen sequencing for multiple diseases, including several cancer subtypes, cardiovascular and immune diseases, COVID-19, and rare diseases. And as of today, we have developed over 70 models and over 19 publications in high-tier journals with our academic partners. We have built a unique federated research ecosystem called the Owkin Loop with top-tier academic centers in North America and in Europe, which enables these secured access to high-quality data sets, engage large communities of medical and scientific experts, and to expand our partnerships globally. And we access this data by installing an on-premise server or cloud solution where de-identified data is transferred. And our data scientists will remotely access this data in a transparent and secured manner. And the data will never leave the institutional firewalls. Only the model will travel, which minimizes the risk of patient data breaches and provides strict control by the institutes. Owkin has multiple ongoing active large-scale federated learning projects with leading medical institutes and pharma consortiums, some of which are shown below. And so based on federated learning and its applicability to biomedical research, we are proud today to present the MIDAS-Owkin workshop, which is separated into 2 sessions. So the first session will cover privacy preservation, methodology, and applications of FL in real-world cases, which will be presented by Ambuj, Camille, Barzan, and Mathieu. And the second session will cover the applications of prediction models and machine learning in biological and clinical settings, which will be covered by Simon, Josh, Alberto, and Johan. And so once again, below are the websites and social media and contacts for both Owkin and MIDAS. Please get in touch with us. We're looking forward to some great science and some future partnerships. And if you do have questions during the Q&As, there's a Q&A box below. Just feel free to type in your questions. And with this, I will hand it over to Ambuj to launch the first talk. Thank you very much.
Thank you, Patrick, for getting us started. Thank you all for coming, and thanks to the organizers of this fantastic workshop. I'm looking forward to learning from everyone. My talk will be on a very recent federated learning project that I did with my students, where we applied federated learning in the context of mobile health. And this is a joint work with my former students, Jessica Liu and Jack Gertz, along with collaborator in Psychiatry, Professor Srijan Sen. So the background here is, as some of you probably know, that mobile health is a very fast growing area within digital health. And the idea is to use mobile phones and wearables to not just monitor, but perhaps even deliver healthcare to the extent that these devices can deliver healthcare. And one of the reasons is that using mobile health helps health providers reach populations even in developing countries where the technological revolution, they kind of leapfrog over the wired connectivity and went straight away to almost complete wireless connectivity. So a lot of people, not just in developed world, but also in developing countries, have mobile phones and even smartphones. At the same time, while this positive thing is happening, there's a negative or very concerning development is kind of this increased mental health concerns across the globe, including developed countries and developing countries. People are talking about the hidden fourth wave after the COVID pandemic, where once the virus is under control, there will be concerns around mental health. And I agree with the WHO motto that there is no health without mental health. So we can't just think about health purely from a physical perspective. We have to include mental health in our definition of health. And I'm particularly interested in depression, which affects over 300 million people worldwide. It's a leading cause of disability. There are lots of barriers, including lack of providers, stigma associated with the diagnosis of depression, and also inaccurate diagnosis, both underdiagnosis and overdiagnosis. And closer to the theme of this workshop, I feel like federated learning provides a very interesting way to trade off two desires, two objectives. One is the objective to personalize to individual people's needs and their individual characteristics. We know that in a lot of health contexts, including mental health, user heterogeneity is tremendous. People vary. People are not identical copies of each other. We cannot just assume statistically that we are getting IID samples when we go across users. So we want to tailor our treatments, our inferences, our predictions to specific characteristics and needs of the user. And this is, of course, part of the broader trend towards precision medicine, where we might tailor things to the genomic profile or to the lifestyle profile or to the socioeconomic status, any kind of information that you have about the user. So while we want to personalize, there is this sort of specter of surveillance and loss of privacy if we have too much digital sensing going on and it's just floating around in different networks without any proper accountability and any proper tracking. People will lose trust in these technologies. And I have a quote here from a former director of National Institute of Mental Health that trust is very important, and part of trust is making sure that people understand that their data is not going to be just released and there are enough privacy protections in place. Lots of emerging technologies in this space. I am by no means an expert on this. I'm still learning. This workshop, of course, focuses on federated learning, which by itself has some built-in privacy, but you can also combine federated learning with other technologies like encryption and differential privacy to get even more privacy. So here's kind of a summary of how we approached this project. We took an openly available mobile health data set, and we sort of wanted to understand the trade-offs between various approaches. One approach is, of course, the standard way of doing machine learning, just collect everything in one place, train one model. You don't get personalization because you're only training one model. You don't have privacy because the data leaves the user devices and sits in a central server, but you can learn from others. This model can actually use data from everyone. So that's the first bullet. The second option is, well, let's just keep users' data on their devices. That if nothing leaves the user devices, we'll just learn an on-device model, one for each user. So that has privacy, that allows for some degree of personalization, but you can learn from others. The third option is you do aggregate everybody's data in one place, but then you build separate models. Okay, in this case, you will have personalization. There will be no privacy, but you can learn from others if these separate models that you're building, they have some sharing of parameters. So some parameters are trained using everybody's data, while other parameters are more personalized. They're trained only using that person's data. And, and then kind of the, what we feel is a golden spot is keep users' data on their devices, build personalized model, but use federated learning, okay? And as we were given a very brief introduction to federated learning, I'll just say, maybe essentially repeat what Patrick already said is, so standard centralized learning, you have data, let's say these are mobile phones, the green, blue, and red, these are phones, they all transmit their server to their data to a central server, which trains some machine learning, typically an iterative algorithm, and it comes up with model parameters. So that's classic centralized learning. Federated learning, and again, federated learning can be done in many different ways with hubs and spokes and complex topologies, but in the simplest setting, you can think of it as kind of a star topology where you have one central server, which is talking to all these user devices. The data, the user device private data, which is in red because it's sensitive, it doesn't leave the device. It is only used to make local updates on the model parameters that this device gets from the central server. It makes some local updates, and these updates are passed back to the server. The server is, of course, getting these updates from other machines too. So it does some kind of aggregation operation on all of the updates. Maybe it's getting data from thousands of devices, and does this aggregation, updates the model, and then this entire cycle repeats. And the big issue in federated learning, and a contrast from classic distributed estimation and distributed statistics, is that there's a lot of heterogeneity. Maybe machines will be sleeping, maybe phones will be charging, not available for backups, for these updates. So this raises a whole lot of new issues that are not present in classic distributed statistical estimation. So just to conclude, I'll show you just basically one slide on methods and the performance. As I said, we used a publicly available data set, so everything here is reproducible fully. Code is available online. There's a data set called the VSAT data set. I'm not going to go into the details because of lack of time. But we basically solve a classification problem of classifying a subject as to whether they are in an affective or emotional state of neutral stress or amusement based on based on data from wearables. So there are 15 subjects. So we don't have a large number of subjects here. It's a very small number. And then we do a comparison between these three models, right? You train an individual model, one for each person, versus one model which is trained centrally, so no privacy. Then we can train that one centralized model in a federated manner. And then we can add personalization, right? Personalization both to the centralized server situation and also to the federated learning situation. And what we found, interestingly, was that there is enough heterogeneity in these people that if you just train 15 different models, one for each person, the overall accuracy is kind of at the same level if you train one global model for everyone centrally with no regards to privacy. And if you try to make the central training a little bit more private by doing it in a federated manner, you lose a little bit of accuracy and you end up doing worse than both of those very basic baselines, right? The 15 individual models versus one centralized model. Which interestingly, and this is the main result of the paper, that if you now train personalized models, so 15 different models with lots of parameter sharing, but with a little bit of parameters that are individual to the 15 models, then if you train them again in a privacy agnostic way, without caring about privacy, then you do improve 92.9% on median accuracy over users, but you don't have privacy. And the interesting thing is that you can do this in a federated manner and get almost the same accuracy. And this was kind of the good result, a nice result according to us. And we have a paper which is under review at JMIR right now, but the code and the preprint are available for anyone to see. Thank you.
Next up, we have Camille Marini from Owkin.
Hello. Is it okay? Can you? Yeah, I think you can see my slides. So hello everybody. I'm Camille Marini. I am CTO at Owkin, and I'm going to talk about a platform for traceable federated learning. that we've built at Owkin. As mentioned by Patrick during the presentation of Owkin, we use federated learning for many projects, and it's something that is important for us. So why is it important? So first, at Owkin, we work with data from hospitals and from pharmaceutical companies. And for many projects, we need to consider data from several centers, because we need a lot of data in order to build an efficient model, and also because we need heterogeneous data to build a robust model that can be transferred to other populations. And second, the reason why we use federated learning is because we work with medical data. And so as you can imagine, medical data is highly sensitive. And so as mentioned by Patrick, in most cases, and even in all cases, the data must remain on the server of their owner. So these two reasons, so the fact that we work with data from several centers and the fact that data is sensitive, made us create a platform for federated learning. And this platform is called Owkin Connect. So it's a product that has two types of users. On one hand, data scientists, and on the other hand, data managers or data experts. This product, Connect, is built around two core features. The first core feature is data privacy. Data privacy, so of course it's ensured by the fact that we use a federated learning settings, but also because we use privacy enhancing techniques to make sure that models cannot leak properties of the data. The second core feature of the platform is traceability. And we believe that traceability is very important in our application, and this for three reasons. So the first one is that with traceability, we can show to our partners what we do with their data. So it brings trust with our partners. Second, it's for reproducibility. With this traceability, it's possible to redo a training of a model and to prove that the accuracy or the performance that was claimed is a real one. And the third reason why we believe traceability is important is to be able to build a fair revenue sharing model. So more precisely, if you can trace the increase in performance of a training iteration, we might be able to build a contribution score of the different data sources. So for now, of course, it's more research topic, but still it's a super interesting topic, and it's something that can be key in the future. Okay, so this product, Owkin Connect, what does it do? So Connect makes it possible to deploy a network of nodes, and in each node, we deploy software that makes it possible to orchestrate and to execute the training of machine learning models with a federated learning approach. In order to make this possible, there are resources for computation and for data storage in each node. And in this example here on the slide, you can see a network of 5 nodes, 4 administrated by hospitals or pharmaceutical companies, and 1 administrated by Owkin. It's a data science node. So in the next slides, I'll present a typical workflow to use the platform. So it's not the only one, but it's a typical one. So a data manager, so either IT technician or data expert, registers his data set only with his own node. So the data set is uploaded to the node and will never leave the node. At this point, he can also define a scientific question that he would like to solve using his data. This is called an objective within the platform. The objective is associated with a test dataset and a metric, which makes it possible to evaluate the performance of a model for this scientific question. So an example of objective is classification, melanoma versus benign lesion, for instance. And in this case, the data uploaded would be dermoscopy images. Once this is done, so once the data and objective are uploaded, so non-sensitive metadata about the objective and dataset are automatically shared with other nodes. So then data scientists can start interacting with a node. So there is no need to connect to the node of other partners. And even in some applications, not all of them, we are not allowed to connect to the partner's node. So she designs algorithms to train machine learning model on the set of distributed datasets in order to solve the scientific question. So she can design any type of algorithm. So it can be a training or an aggregation algorithm, and she can really tune it. So in order to be able to do personalized federated learning model or a simple federated model. She also designs the plan to create the machine learning model from this algorithm and this data. This corresponds to the design of a compute plan. So it's a specification of training, aggregation, and evaluation tasks that are executed on the data. So the platform is really flexible. It can handle any chain of training, aggregation, evaluation task with any type of algorithm. So once this is done, once she has designed her algorithm and compute plan, she registers both the algorithm and the compute plan to the platform. And then she has nothing else to do. The platform handles the computation automatically. And at the end, there is a model, which is an output of the platform. So I'm going to skip this to keep time for the technical description of the platform. So first, Owkin Connect is built with an open core approach, meaning that there is an open core and then there are additional layers which are proprietary. So we decided to adopt such approach, so using an open core approach for 3 reasons. First, to ensure trust with our academic and also pharma partners, so they can audit the code if they want to. Second, to increase the robustness of the code with the participation of the open source community and to ease the collaboration around the code within our collaborative project. And the third reason is because we hope to benefit from use cases in other verticals to become the standard for privacy-preserving distributed learning. So the open core is called Substra. So the code is hosted by a foundation, the Substra Foundation. So you can check the GitHub, which is there is a link on this slide. And the code for now is mostly designed and implemented by Owkin. So this open core corresponds to a framework for machine learning orchestration on sensitive data. It includes the setup of a network of nodes, trustless traceability and orchestration. And in order to do so, we use a distributed ledger technology. So I've seen that someone asked the question about using a blockchain for federated learning. So this is what we do. We use a distributed ledger technology, which is called Hyperledger Fabric. Then in the open core, there are also code to manage the execution of machine learning tasks and very simple programmatic interfaces. And then on top of this, as proprietary layers, we have much better interfaces for data scientists. And we also have libraries for machine learning algorithms, data preparation, and also privacy preserving methods. So on these slides, you can see an overview of the architecture of the platform. So I'm not going to go into the detail of it, but I wanted to point out, so this distributed ledger technology that we use, which is called Hyperledger Fabric. And using this, there is a distributed ledger, which is shared across all the different partners. And this ledger stores non-sensitive metadata about the datasets, the algorithm that are pushed, the objectives that are pushed to the platform. In particular, there are permissions associated with each asset. The ledger also stores the details of a compute plan, so of the set of training, evaluation, and aggregation tasks. Okay, so now I'm going to present two key concrete applications where we are using this platform. So the first one is called HealthChain. So it's a project which is funded by the French Banque Publique d'Investissement. And the goal of this project is to build and to deploy Connect and to apply it in two different fields, oncology and fertility. It's a big consortium, HealthChain, of two startups, one in oncology, Owkin, and one in fertility, Apricity. Two academic research centers, École Polytechnique and Paris Descartes, and 7 academic medical centers. Owkin coordinates the project. It started 2.5 years ago, and it's going to end in 6 months, I think. So at Owkin, we've built a platform that is currently deployed in 3 centers. So Centre-Léon-Bérard, Institut Curie, and CHU Nantes. And so it means that the platform has been deployed behind the firewalls of these 3 centers. And in order to do so, we had to create strong security documentation and to successfully pass security audits. So now that this is done, our data scientists work on building predictive models of treatment outcome for breast cancers and predictive models of image classification for melanoma. They already have nice results, and I think they are going to be published soon, so stay tuned. And so this was the first project. And there is a second project, which is called Melody. And it's so this one is different. It's with pharmaceutical companies and not with medical centers. So it's a project which is funded by the European Commission and by the European Federation of Pharmaceutical Industries and Associations. The goal of this project is to apply federated learning for drug discovery with data of 10 pharmaceutical companies. So you can see the logo of these pharmaceutical companies here. So here again, Owkin coordinates the project, and it started 1.5 years ago, and it lasts 3 years. So
thank you, Camille. We have to start the next talk. So maybe like,
yeah.
If you can wrap it up in a couple of seconds, that would be great.
Yeah, I can do that. So what I wanted to say is that so these two concrete applications of the platform, we learn a lot when doing this application. And the key learnings are that security is key. Partners don't want us to deploy unless we can prove through security audits that the platform is secure. And the second point, the second key learning is that it's super difficult to build algorithm without having access to the data. So hopefully in some cases we have access to equivalent open data or to a subset of real data, but it's not always the case.
Thank you very much. I appreciate it. So we leave the questions for the panel. Thank you, Camille. And Barzan, can you start sharing your slides?
Perfect. Well, good morning, everyone. Thanks so much for joining this workshop. I'm I'm an associate professor at the university in the computer science department at the University of Michigan. And before talking about the research, I have to, I'm contractually obliged to thank those who've been paying our bills. So National Science Foundation, Google, and MIDAS itself. And all of the work I'm going to be presenting is the great work that my PhD students are doing, and I'm just here to take credit for it. In particular, I'll be focused on presenting the line of work that one of my PhD students, Ray, has been conducting, which is on accelerating machine learning with Bandit. But for those of you who are interested, I'm happy to put you in touch with some of my other PhD students who are working on distributed meta learning or large-scale zero-shot learning, whose work I'm not going to be talking about in this talk. But as I mentioned, most of the work I'll be presenting today are based on Ray's research. And just to put a quick plug here for him, he's going to be on the job market next year. So if you guys are looking for an awesome, super smart machine learning expert, you should reach out to him. So a couple of words about my research. So I'm leading the PHASE lab, which stands for Fully Autonomous Infinitely Scalable Systems. Our line of work is mostly along two dimensions: accelerated query processing, where essentially you can write, think about writing SQL queries. How can you take those SQL queries that are taking hours or minutes to finish in a couple of seconds? So we've done a bunch of open source work in that area. Some of it has already been commercialized or acquired by other companies. But I'll be focusing on the second line of work from our lab, which is on accelerating distributed machine learning. I think there's a typo on the slide, I apologize. But anyway, zooming back, I think the demand we're seeing, I know the theme of this talk is on federated learning. I don't think we have a project on federated learning, but I want to just talk about this line of research we've been pursuing on accelerating machine learning. And the current trend is that enterprises are essentially collecting more and more data, whether it's healthcare data or digital data, mobile data. And the current trend is that as we're collecting more data, there's this temptation to actually create, there's this need to create larger models to sort of encompass the information that that's in that data. And that way we can actually get to higher accuracy. But that essentially means more parameters in our models, and that means our training is becoming more and more expensive. So on the right, I'm borrowing a plot from another paper where they're actually showing how the state of the art essentially has improved accuracy, but at the cost of significantly more operations, multiplications or addition operations for the neural net that they're training. So that's the trend that we're seeing in the industry and academia. So that's the rest of this talk is going to be about how we can actually reduce the number of operations to make machine learning at scale more viable, more eco-friendly, but also more affordable. So here's one key idea that I'll be talking about throughout today's talk. How can we use multi-arm bandit for accelerating machine learning? And so for those of you who are familiar with this, so multi-arm bandit is a nice framework that studies a trade-off between exploration and exploitation in settings where you need to make some sort of decisions. And the idea is that this actually being able to make the proper decisions in many settings within machine learning can actually lead to speeding things up or reducing computation. So I'm going to walk you through a few different examples that we've explored in our research between coordinate selection in maximum inner product search, example selection for deep learning, gradient compression in distributed learning, and for those of you who are interested, we also have some ongoing project about client weights adjustments in federated learning. But let's just get started on the main topic. I don't think, I have to apologize. I actually was under the impression that the talks are going to be 20 minutes. So I'll get to the first two examples. So for those of you who may not have heard about bandit models, so here's a pretty high-level, quick recap of what multi-arm bandit is. So the idea is that basically you have to make a bunch of decisions. You have n different decisions or actions you can make. We call these arms over t rounds. And then you receive, each time that you pull one of these arms, you receive a numerical reward. And the goal is typically one of the two. Your goal is either to find the best arm with as few pulls as possible, or within the T rounds that you have, you want to accumulate as many rewards as possible or maximize the reward. reward that you're going to get. So let's see how you can actually formulate a number of different interesting machine learning problems to speed them up using bandit models. So exploration, the idea is that you always have this dilemma that should I try out a new arm to explore whether they have a higher reward or not, or should I just exploit the information I already have about some of my existing rewards? So let's take this example from Maximum Inner Product Search, which was published in 2019's AAAI. So here's the MIPS problem, or the Maximum Inner Product Search, right? So you're given a vector collection, let's say n vectors, small n, and each of these vectors has n dimensions, for capital N, right? And the goal is, given a query with the same number of coordinates, we're trying to find the data point, a vector in that collection that maximizes that inner product, right, with the query. This is an important problem. A lot of recommendation systems have to solve MIPS to find the best item to recommend for a user. In multi-class prediction, you also have to solve MIPS. So MIPS is kind of an operation that appears in many. It's a pretty important and common subproblem that appears in many different settings. So here's a naive approach to solving this problem, right? You can just go and actually compute the inner product for all those vectors given any new query, and then the time complexity is going to be obviously the order of n times n, which could be too costly when your vectors are high dimensions, or you have too many examples, right? So either small n or capital N is large. That naive approach is not really scalable. So the goal here is to see if we can actually solve this problem efficiently and approximately. So here's the main idea. It would be good if we could actually, instead of calculating the entire inner product, we could just calculate the partial inner product, and somehow use that partial inner product to identify the optimal solution, the optimal vector, with as few multiplication operations as possible. So here's how you can actually cast this as a multi-arm bandit problem. So you can actually say that, well, look, I'm going to treat each of my vectors as an arm, and the reward list, I'm going to assign a reward list which, corresponds to the multiplications of its corresponding coordinates with the each of its coordinates with its corresponding coordinate from the query, right? So then you have a finite list of rewards, and then the true mean of each arm then obviously is the average of these coordinates, this inner product that we're trying to estimate, right? Because if we had that exactly, then we could easily, return the optimal solution. So here, the idea of pulling an arm would be essentially getting a reward sampled without replacement from this reward list, right? So every time you're pulling a reward in this case, you're essentially saying, go and pick one of the coordinates at random from all these n coordinates, and then multiply it with its corresponding coordinates from the query, and do this without replacement. Now, the goal is, how can we identify the best arm? Because if we find the best arm where the mean of these coordinates times the query is maximized, then the inner product is obviously maximized as well. So to solve this problem, we need a new setting, which we call the multi-arm bandit setting, with a bounded number of pools, right? Where you have a finite number of pools for each of these arms. And this way we can actually solve the bandit problem. So let's call this the MAB-BP, not a very pronounceable name, but here's how you can actually solve this, this bandit setting, right? So you basically start with n arms. You have, you're given an epsilon and delta. As I showed on the previous slide, our goal is to return the optimal arm with, given any epsilon and delta, prove that with probability at least 1 minus delta, we return an answer that's within epsilon of the optimal arm. And the user can choose epsilon and delta to trade accuracy for performance. So you initialize the average reward for every arm initially with 0. Then you essentially pull every arm a certain number of times. There's some sort of math that governs how many of them how many times at each round you have to pull each of these arms. In other words, how many coordinates you need to look at random. That will actually ensure that after each round you can eliminate the bottom half of the remaining arms, the remaining examples, and then just continue with the other half, and continue this process until you're left with only one arm, right? So you can actually show, I'm skipping this result pretty quickly, but you can show that this algorithm would actually, will guarantee that you can always return the epsilon optimal solution with a probability of at least 1 minus delta. and each arm is never going to be pulled more than n. So you're never going to be actually worse than the exhaustive solution either. But in practice, you can actually see significant speed up for any level of precision or speed up that you're looking for. So it gives a pretty explicit knob to the user to control these. So my intention was to actually walk you through how to use bandit models to speed up ADAM for deep learning, or how to actually use multi-arm bandit for also doing gradient compression in distributed learning. But I think we're already at the 11-minute mark, so I'm gonna skip the other two parts, and I'm happy to talk about how the other remaining directions either offline or during the panel. But just to be mindful of time, I'm just gonna skip to the conclusion, and I think probably it's a good idea to flash some of the okay. So the idea is that I think we've just, even though there's been some work on using multi-arm bandit for speeding up and accelerating machine learning workloads, I think we've just started to scratch the surface. There's a lot of situations where training large-scale models in a distributed setting or in a federated setting, or when you're doing it, doing your computation in the edge or on mobile devices, there's a lot of computations and network communication that you can actually minimize and avoid if you actually use some form of multi-arm bandit, and these were some of the examples that I talked about in this talk. Obviously, we only got to talk about the MIPS one, but we have a New York paper on using bandit models for example selection in ADAM, as well as some ongoing projects for reducing the network communications or speeding up federated learning. But with that, I think I'm 16 seconds over my allotted time. Thank you so much for tuning in, and I look forward to your questions during the panel discussion. Thanks so much.
Thank you, Barzan. I appreciate it. Matthew, can you share your slides?
Oh. Can you see my slides?
Yes.
Okay, thanks. Hi, everybody. My name is Mathieu. I'm working at Owkin. Today, I'm going to present you a work that we did on the application on federated learning to histopathology datasets. It's a joint work with my colleagues Jean, Constance, and Eric. And the goal of this work is really to understand the different changes that one faces when applying federated learning to real medical data and propose solutions. So I think I'm going to skip this part because judging from the previous presentations, the motivation for federated learning is getting quite clear. So we want to have access to a lot of data, but the clinical data isn't always easy to share. And so we are in a setting where different institutions want to collaborate to perform a common machine learning training, which is called collaborative federated learning. And I refer you to the publication of Ricky and co-authors, which delves more into this exact setting. So in this work, we are looking at histopathology data. Histopathology is a branch of biology studying tissue using microscopy. It's the gold standard for understanding disease, notably to classify the cancer grade of patients. So in this work, we're looking at a machine learning task of tile classification. So we have access to different slides of patients, of tissue patients, which are pretty large. It's about 100,000 pixels times 100,000 pixels. And the task is given a very small region in the slide, a small image that we call a tile, is to know if to predict if this tile belongs to a tumorous region or not. We have access to this information because this slide was previously annotated by an expert. And so in this setting, which is a bit simplified, but allows to grasp the main problems when one does federated learning on real data, we are in a setting where we want to predict a label, it's a binary classification from an image. And we're gonna look at the use of deep convolutional neural networks to solve this task. So because we're in a federated learning setting, we have slides coming from different centers. And as soon as one looks at the slides, we see differences in distributions of the different slides. Here, this is an example from the Chameleon 17 dataset from these authors. And what you can see is that the colors are different. When you look more in detail into the distributions of colors, you really see differences in the histograms. But in fact, it's not only variations in the color distributions. You can also have a lot of different factors of variability, such as demographics, biopsy preparations, the preparation of the slides, their digitization. And also, since cohorts were selected by different PIs, maybe for different studies, they may vary. So, and in fact, this heterogeneity may negatively affect training. There are references in the literature, for instance, FedProx here, which shows that federated learning can fail in these settings. So I'm talking about federated learning. So let me give a little bit of technicalities here. So we consider the simple case of the star-shaped approach that was mentioned before by Ambush. And what we consider here is a machine learning problem where we have different local datasets K with the input, which is the image, and the label Y. And the goal is to minimize the global loss function, which is simply a weighted loss of the different local losses, which are just the empirical risk. So a simple approach to solve this problem is to do back and forth between the central aggregating node and the different centers as follows. It's called federated averaging. You start at each round. The aggregator sends to the different centers the current value of the neural network weights. These weights are then refined by the different centers on their local data, and then sent back to the aggregator. And finally, the aggregator performs a weighted sum of the weights, giving rise to new values of the weights. Okay, so this is the setting, and we'd like to apply a neural network to train a neural network in this setting. It's supposedly simple, but in fact, we encountered not only issues related to heterogeneity, but also related to the architecture that you wanted to use. In fact, we had an issue with a crucial neural network layer, which is called batch normalization. It's a layer which is used in almost every modern CNN architecture for end-to-end training, and it's really crucial to achieve a good performance. This layer works as follows. Given an input tensor X, it first performs a renormalization of the input by some mean mu and some running variance sigma, and then it rescales the resulting normalized tensor by multiplying by some weights gamma and adding some bias beta. So there are 4 kinds of parameters in this layer, but they do not play the same role. Mu and sigma are what we call batch norm statistics. They are running means and variances computed across iterations of the inputs, while gamma and beta are standard trainable parameters. It's important to point out that because here the mu and sigma are running means and variances, batch norm is ill-defined in the federated setting, in the sense that computing F, the neural network on all the batch coming from the different centers is not the same as computing it on the individual entries from the different centers and concatenating them. So we are definitely not, as soon as we introduce a batch norm layer, we break a little bit from the standard federated learning approach. It would be possible to retrieve exact pool equivalent computations by communicating all intermediate activation statistics, but this is completely unfeasible from a communication and privacy perspective. So a first solution would be to do the same approach as federated averaging and simply periodically average the batch norm weights and the batch norm statistics, breaking from the pooled setting. So we have tested this approach on the Chameleon 17 and 16 datasets. And here we report the average AUC. So it's a metric which measures the classification performance. Higher is better. And what we can see when we compare the approach where one trains with all the data available and in the federated setting, that federated averaging on a network with batch norm layers gets a very bad performance. When we compare with the control setting where on a network which doesn't have batch norm layers, we see that we are able to get quite a good performance. So this is really due to the way we handle batch norm layers in in this algorithm. So to circumvent this issue, we borrowed an approach coming from the domain adaptation literature called adaptive batch norm. Adaptive batch norm is an approach to transfer a neural network trained on a first domain to another one, and it simply does it by recomputing new batch norm statistics on the second domain while keeping the rest of the neural network's parameters unchanged. This has been shown to improve the performance of the neural network trained on a first domain, for instance, one of the centers, to a new domain, the other center. And here, this is an example from the authors, where they show that for cloud segmentation in an image, you get a much better performance with the approach. So the lesson from this approach is that batch norm statistics are tied to a given data distribution, while other neural network weights can be exchanged between domains. So we borrowed from this approach to propose our method, which we call SiloBN, we propose to keep batch norm statistics local during training while exchanging the batch norm weights as well as the remaining batch norm neural networks parameters. There are two benefits to this approach. The first is model personalization, because each center will have individual batch norm statistics. It will be better handle the heterogeneity between the different data sets. And then there is another benefit in terms of privacy, because the amount of shared information will be reduced compared to a naive federation of batch norm layers. We have tested this approach on the same benchmark as I presented before. So this has the previous results with the same metric. And when we plug in the SiloBN approach, we see that we're able to get a good performance on a neural network with batch norm layers, with numbers which are comparable to what one gets without any federation or when one has access to all the data locally. We have also made an experiment to compare with the transfer, so inter-center generalization. We trained on 2 different centers from the dataset Chameleon 16, and we then evaluated it, the resulting network, on the 5 different centers from Chameleon 17. And to transfer it, we use AdaBN in the case of SiloBN. We compared ourselves to the baseline federated averaging approach. And what we can see as these results is that on average, we improve the transfer performance with respect to other centers. So to sum up, in this small work, what we tackled is the federation of a machine learning model on histopathology data. We had 2 challenges. The first one is the data heterogeneity. The second one is the federation of a batch norm layer, which was not trivial. So these are but a small part of all the open questions which exist in federated learning. There are also very important questions in terms of privacy, in terms of communication, cost. And not only on the machine learning aspect, but also in the systems aspects that Camille, for instance, was mentioned before. At Owkin, we're trying to build a federated data science workflow, combining machine learning and systems, and we hope to be able to make new scientific breakthrough with this federated data science workflow. Thanks for your attention, and I'd be happy to answer your questions during the panel session.
Thank you, Matthew. Now we essentially start the panel section of that, which will be attended by all the speakers and Dr. Kandeep Singh, who's a member of the panel right now. So I suggest that we start with looking at the questions that we received in the chat, and then open it to the entire group to ask questions. I would say that the type of questions that we're getting are centered around 2 aspects of using federated learning. One of them is the privacy of these models, and the other one is like learning capabilities with regards to the statistical heterogeneity of the data in different units. So I'm going to start looking at the questions that are posted on the chat that deal with the privacy issues. So the first question that we have is, could you please tell more about Owkin security audit? And they mentioned a couple of specific attacks, and they're talking about the type of attacks that have some level of knowledge about the data sets that are used for creating the model. I would ask Matthew or Camille to respond to this, if you like, because this is something related to Owkin.
Yes, thank you. I mean, I can take this one. So about the Owkin security audit, so it's audits which are not performed by Owkin. It's performed by external companies which are specialized in cybersecurity. And so, depending on the use case, the audit can be either an audit of the source code. So they're going to review our source code and make sure that there is no flaws in it. The second type of audit that we went through was pen testing. So basically, we deploy our application in an almost real setting, apart from the fact that we are not going to use real data, but for this case, we use open data. And then security experts try to attack the platform, either in a black box approach or in a gray box approach, meaning that black box approach, they don't have any information about the platform and any access to the platform. And gray box, they can behave as being one of the members of the federated network.
Thank you. So before we go to the second group of questions, or maybe for a pause for technical questions, we have a question from Drew Bennett. He's asking, can you describe briefly the IP ownership approach to the models? And that's sort of related to another question that I have. Just think of every entity, especially if they're hospitals and banks and others. They consider their own data an IP, and they're not going to share it just, that obviously they're not sharing the data, but they're sharing the model. But the model which was developed based on the data that they have is also related to the IP that they have. So right now, for example, if you go to University of Michigan to say that I'm going to develop a model, one of the models that you use in federated learning, using the data that University of Michigan has, the model that you use, and then you average it, aggregate it with other models coming from other centers. This model that comes from University of Michigan, it's a almost impossible challenge to get the IP. You need to go through the entire regular process of IP. And if you have multiple entities involved in it, you have 15 different hospitals, the IP model that you use to create such a system is something that needs a lot of discussion. So I guess Drew's question is basically focusing on that and asking you how it's open to all participants. How do you want to deal with that? Anybody wants to comment on that? Maybe Owkin starts with Matthew or Camille or Patrick. Do you have a comment on that?
Yes, so I'll try to address this from a partnership perspective. So in regards to IP ownership, it will of course depend on the types of legal agreements that we have with the universities and with whichever pharma companies that we're licensing these models to. All of these specific IP distributions will be declared in a master collaborative agreement of who owns the IPs, and for it will be project specific again, and all of these specific details regarding ownership of model enhancements for federated learning projects, all of that will again be project dependent, and I'm happy to go through the details of the business development points and the legal perspectives separately, and maybe we can share some more details there.
Thank you. We have another question, again, goes to the privacy concerns. And the question is, many of the deep learning models, they have some mechanisms to actually sort of encode the weight or use steganography for the process when they're sharing these weights with each other. The question again is for Owkin. How do you handle that? Are you considering doing that? Are you doing that in your platform?
Yes, I can take this one if you want. So regarding GAN and autoencoder, yes, it's perfectly true that this representation learning, especially in the early layers, you can take part of the underlying data. So what we can do in this case is to apply some kind of differential privacy obfuscation mechanism to reduce the sensitivity of the neural network to the underlying data on which it was trained, for instance. Also, a more simple approach is not to train the representation learning part on sensitive private data, but maybe train it on public data and use something which is pre-trained, which is then won't carry out this data.
All right. Thank you. And more questions. I mean, we keep getting questions related to different aspects of the privacy for this, which is, I understand that this is a major factor in using federated learning. And this question refers to a paper that was recently published, and the authors showed obtaining secure data is possible. They're talking about federated learning strategies that can be used to handle this type of situations. Would you like to comment that, anyone? This is not related, this is not specific to Owkin, so anyone wants to comment on that?
So maybe I can comment related to the strategies on backdooring federated learning, where one wants to use or really steal data in some way. So most of these approaches rely on in a setting, in a mobile setting, where one can hack the mobile. In Owkin's case, we do not have that many actors. We don't have millions of devices which can be corrupted. We have a few of them. And because we're using a very secure framework, it's quite difficult to enter it and to modify the input. So that's a piece of an answer.
So I'm going to ask a more general question. I know that, Matthew in his presentation showed us some techniques that he tried to somehow consider the statistical characteristics of entities into the weights of the neural network when we're averaging them. But in general, I think a concern that we've seen in the past regarding the use of methods like federated learning has always been that if you have heterogeneity in a statistical distribution of the entities, that multiple entities that you use for federated learning, knowing how to directly incorporate the differences of distribution of different classes among these units into the overall model, that the average model that you're creating, has been a major challenge. Like the simple using NK over N for the weight of the models haven't worked for many cases in the past, and showed that this is statistical biases. There is no IID, there is no independently identically distributed assumptions that you can actually satisfy in these cases. So what I'm thinking is, I ask for the panel and all members of the panel is, how do you think this can be, the methodologies, the new approaches to handle with that? Do you think multitask learning or methods like that can at least partially address that, or it will remain to become the major challenge for federated learning? Any member of the panel? Barzan, you were using some technique that I think might have some potential to address that. Would you like to comment on that? And I see Karandeep has some comments about that as well.
Go ahead.
Sure. Yeah, maybe I can make a comment on this. So I feel like because the heterogeneity in the client data, for example, the data might be different from different clients, and also because participation level from clients might be different. For example, some clients might participate more frequently in the federated learning setting. So I guess, yeah, I agree that it's very important to adjust the weights of the clients. Maybe we need to learn the weights essentially. So that's why. So I think that maybe we can use a bandit to learn the weights of the clients when we aggregate the gradient from different clients. And so a good thing about bandit that it can deal with the trade-off between the exploration and exploitation. This is because at each round, only a small subset of the clients are participating in this round. And so we are faced with this dilemma between the participation of the clients. So I guess, although I'm still exploring this direction, but I have the intuition that bandit could be helpful in designing a better strategy to designing a method of aggregating the clients by adjusting the weights for different clients.
Thank you, we appreciate it. Karandeep, you wanted to add to this discussion?
Yeah, and I think what I wanted to add was something, I think the discussion so far has really been around privacy as a major issue. But I'll just say deployment, is a major issue as well. And one of the challenges, so I'm involved in a project where we're building, early warning systems using EHR data across a network of 30 hospitals, where we are federating at the level of the health system. So within the health system, they can pull data. Between health systems, we would like to not share data, but share intermediate models. And so I think what I was saying is that I think any approach that we use in a health setting has to be account for local calibration issues. The patients who are seen at University of Michigan are not the same, level of acuity, or are more sick in general than a patient seen in a community hospital. And so, like, for example, one of our partners is Cleveland Clinic. And so they have a main hospital that sees very sick patients and a set of community hospitals that sees less sick patients. So even though within their health system, they can pull data, even though they can, they probably shouldn't, because, or if they do, they need to take into account that the local calibration is going to be different at those places. And it's probably not going to be simply accounted for by including how sick the patients are, because there's local differences in practice between hospitals. So I think, the approach I'm working on is a federated stacked learning approach, which has ability to encode local calibration into the model. And it has two levels of modeling, a local level of modeling and a global level of modeling. But I do think that, similar to federated learning in the space of mobile devices, where individual people are different in their relationships and their weights and coefficients, the same idea is true in the setting of hospital to hospital variation, or variations between a patient admitted to a medical floor and a surgical floor, and their risk of needing ICU level care. And so I think some of these ideas from how to calibrate these models in a pooled approach need to be transferred to federated approaches as well.
That's an excellent point. And I think, when we apply such models on health applications, with the next step of the next session for the workshop is biotech and medical. The issue of looking into these biases and methodologies like the one that Karandeep mentioned would become really, really important to take care of these statistical biases in the client unit level. we have another question that is talking about yet another, typical concerns on use of the federated learning. And I would say this concern that is dealing about the communication cost may be more significant if you're dealing with, mobile systems, but for the applications in hospital, I'm not sure how important would be to have, that as a major factor, considering, the size of the data and the frequency of usage of the system. But let me read the question, and Owkin, it's again a question addressed to you guys. You can answer it. Is communication cost an important concern in the projects of Owkin? Will a one-shot federated learning algorithm be preferred to multi-round one at cost of extra computation, say? So any Owkin participant can answer this question, please. Camille or Matthew or Patrick?
Yeah, sure. So it's something that is important for us because, of course, I mean, if you reduce the size of the model updates or if you reduce the number of updates that you need to do, then you can run more federated learning optimization, and then you can explore more spaces and try to better optimize your algorithm. So of course, I mean, so yeah, I agree. It would be great if we could reduce this.
Thank you. I think we have another question that goes back to the statistical, properties of and like quality of learning in federated learning. The question is, it seems that it would be difficult to detect quality issues in the data from a center if the data can't be reviewed centrally. How do you address that? So can anyone discuss the methodologies that we are using to handle that? So basically, if you just leave it for the client to decide about the quality of the data, you may end up like getting a garbage model trained with garbage data. But how do you create some guidelines or something to do that?
I can share what we do. I put an answer in the chat. I'm curious to hear what others have to say. We have basically a three-part process. One part is that we enforce a common data model. So I think that the first thing is what any variable means has to mean the same thing at different sites. Just because you're not pulling data doesn't mean you don't need to have common definitions. The second thing is our model code that we share. So we have a shared code base that we distribute out to everyone. Prior to it ever training a model, it extracts aspects of like data plausibility, consistency, and missingness, so that if there are outlier centers, we can kind of identify what issues are and figure out what we need to audit or prioritize aspects of data and centers that need to work on some audits. We have kind of a process where we have planned meetings for folks to actually do the audits. And I think, yeah, even with all that, in our approach, we have essentially a center-wide cross-validation where you can consider each site's model gets a sub-model gets evaluated everywhere else. And so if there's clearly one model that performs terribly everywhere else, we can assume that there's something different about the underlying data, or that it's a much smaller data set than the other sites. So we actually have our method has a built-in way of identifying kind of centers with underlying data problems, because those models won't perform well when we cross-validate them. And I use cross-validation in a different sense. I don't mean like tenfold. I mean treat each center as a fold in a sense. So if that model does poorly at every other center, there's some issue probably in the underlying data.
Thank you, Candy. We have maybe 1 minute before we go to the next session. I just wanted to ask Candy, since Candy has been using this federated learning for a larger scale medical applications, I think if Candide can tell us a little bit about the challenges and lessons that he has seen so far in their application, that would be a perfect segue to the next session, which would be biotech and medical applications. So Candide, can you explain a little bit more about your projects and what you had to do to properly use federated learning for your application?
Yep. So our work is underway. I don't have a publication to point to that you can look at right now describing the work, but we're kind of in the midst of doing it. The challenge really was that we are aggregating data across centers in the U.S. And it's a collaborative of 30 hospitals belonging to 4 health centers that don't share a common EHR, aren't part of the same research networks. So we don't have an underlying common data model that we can rely on. And so I think that the same challenges that have been dogging medicine since very early on or health informatics research, which is, how do you, even if you were going to pool this data, you'd have to adhere to some kind of commonality. I think that central fact, is still very much the same challenges we face today. We've got OMOP, we've got PCORNet, we've got other, research-oriented common data models that have been circulated with kind of incomplete adoption. And so I would say for all the fanciness in the methods and everything else that we do, when you're talking about healthcare data at scale, and if you're not talking specifically about imaging, where we've maybe got some DICOM standards or that exist, but we're talking about EHR data, there's just heterogeneity in how things are documented, how things are represented, what codes different places use to represent the same kinds of procedures, that it's really a very basic issue that I think we're still dealing with. And so it's been tackling those basic issues that have led us to be able to do more powerful work. And I think deployment is underappreciated as a problem. You can do all kinds of crazy cool research with modeling, and then that model dies the moment you try to get it into the EHR. And so we've really been putting a lot of effort at University of Michigan in being able to build custom models into our EHR and have them run kind of on regular intervals on large swaths of patients.
Thank you. I appreciate that, Candy. So now we are entering the session 2, which is focusing on biotech and medical applications. Maybe I should ask Simon to start sharing the slides.
Hi everyone. So I hope that works. My name is Simon Gégou. I'm a data scientist in the medical imaging team at Owkin. And for this first talk of the second session, I will present you a work we've done on a prognosis model for hospitalized patients with COVID-19. So I would like to start this talk with a personal anecdote to remind you how peculiar was the context last year. So at the end of February in France, as you can see on this curve, there were only 100 cases of COVID in France. And in the first day of March, I went to north of Laponia with some friends for a ski touring expedition. And within just 2 weeks, so there we did not have any mobile network and we did not see anybody for 2 weeks. And when we came back, it was like complete chaos. All borders were closed and there were hundreds of people dying every day in France. So I called my colleagues at Owkin, and there everybody was trying to help for this crisis. And a question back there was, what are the different risk factors for patients hospitalized with COVID? So we reached out to our partners, and some of them were very interesting in getting to understand what is the particular role of imaging. So the initial questions we had was, what is the added value of imaging in the prognosis of hospitalized COVID-19 patients compared to clinical and biological data only. So we created a consortium with 2 hospitals and another university in France. And we gathered data from 1,000 patients with clinical data, biological data, radiologist report, and imaging. And it was impressive to see all the different teams working very fast on every aspect of the project. And so within 2 months, we had multimodal models called AI severity, and we also benchmarked this model against other scores which were published in the literature. All the project has been open sourced, so I put the link to the code here. It's on GitHub, the Owkin GitHub repository. We also published the preprints, and the publication was peer-reviewed and should be published in the next few days. So in imaging for COVID, the main modality used is the CT scan. So you can see here on the left a normal CT scan with the lung with full field of hair, and on the right CT scans for a patient with COVID. So you can see a lot of white spots which corresponds to different lesions. So back there in March, it was already quite clear that CT scan should not be used as a first-line diagnosis tools, because it lacks of specificity and sensitivity in the diagnosis. But anyway, in many countries, there were a lack for PCR tests. So many practitioners did use CT scans before they get enough material for PCR. And it was already known that the amount of lesions in the lung, so the roughly the amount of white on the CT scan, was by prognosis biomarker, and we were wondering how much and how does it compare and how does it complement with other clinical and biological data. So we partner with 2 hospitals, Hôpital Kremlin-Bicêtre, so KEB, and Institut Gustave Roussy, IGR, which are 2 hospitals here in Paris. Following their advices, we define severity as the death of the patient or a need for high ventilation or O2. And we decided to exclude admission to intensive care units as a severity factor, mainly because it's a hospital-dependent decision. So first, we performed a univariate analysis on the 60 variables we collected. And what we found is that oxygen saturation and age were very associated with severity. Also markers of inflammation, so secondary to the innate immune systems, such as LDH or CRP. And indeed, we found that the extent of the lesions in the lungs, so the disease extent, was well correlated with severity, as well as a radiological pattern called crazy baby. So to build the multimodal models, we started first by splitting the data into a training cohort with patients from KB and 2 validation cohorts, 1 in KB, 2, and we use all the patients from IGR to be in a second external validation cohort. We started to build a baseline model, so simply a logistic regression based on clinical and biological variables only. So of course, we tried the whole armada of machine learning models, such as like XGBoost or Random Forest. But as it didn't bring that much performance, we preferred to stick to the simplest model. And we performed all these experiments on the KB development cohort. To see if the radiology added value to the prognostic model based on CNV data, we used 3 different models for radiology. The first one was based on the radiologist report only. The second one was based on an automatic segmentation algorithm, which automatically segmented all the lesions of the scan. So to develop this model, we needed to annotate scanners to say to the algorithm where are the lesions. And we also developed a third algorithm, which didn't need annotations and tried to directly predict from the CT scan the severity of the patient. So this model is called AI severity. And then to combine the radiology models with clinical and biological data, we combine the output of the radiology model with the few variables, few clinical variables, biological variables. So a quick focus on the AI severity model. So it's deep learning models, which consist of 3 steps. The first one is a segmentation of the lungs on the CT scan using a UNet. The second one is 2 feature extractors that we use for each of the slices. The first one is a ResNet50 that we pre-train using a self-supervised learning method called MOCO on 1 million external CT slices. And the second one is an efficient net pre-trained on the ImageNet dataset. And the output model was logistic regressions followed by averaging. So here again, we tried a bunch of things and took what was the simplest, like a balance between simplicity and performance. So here are the results for the multimodal models. So there are 2 rows. The top rows corresponds to performances on the KB cohort, and the bottom row corresponds to performances on the IGR cohort. And you have 3 different columns corresponding to 3 different outcomes. The one on the left being the severity I defined earlier. In gray, there is the results for the model based on clinical and biological data only. And the 3 other ones are the multimodal radiology models. What you can see here is that we have indeed an improvement over the gray box for most of the data sets and outcomes. However, the improvement is modest and often non-significant. First, because we had small data sets for validation, and also because what we saw is that there is a high correlation between the imaging features associated to severity, such as the extent of the lesions on the CT scans, and the markers of hypoxia, such as oxygen saturation, or inflammation, such as LDH, or CRP. We also benchmarked our models against existing risk scores. So we also open sourced all the benchmarks so that people can use it, because all papers did not provide source code. And here, the AI severity model, which is the one with the highest performances, outperformed most of the models we benchmarked. So finally, we had our answer regarding the added value of imaging. So it seems it can help, but the improvement is not that big because of correlation with other markers you can get with a blood test or with the clinical variables of the patients. We worked also with a researcher from IGR on how we could deploy this model in practice through a nomogram. So the idea was simply to associate each new patient with a risk, with a score between 0 and 100. Each score is associated to one group, which are the 5 quintiles of risk on the test data set. So if you have a new patient, you can see in which group he is, and then what were the outcome for the patient during the first wave of the pandemic. So of course, to use such a model in clinic, you need FDA marking to use it.
Hey, Simon, you just wrap up in the next 30 seconds, please. Thank you.
And if you want to extend such model in other centers, you would have to calibrate these models and validate on additional external data sets. Thank you.
Great. Thank you, Simon, for that great talk. Next up is Dr. Josh Welsh. If you could please project. Thank you.
All right. Hi, everybody. Thanks, Patrick and Jing and Kayvon for organizing this great workshop and for inviting me to speak. And I'm really excited to talk to you about some of the things that I've been working on lately. It's a little bit of a change of topic, but my research focuses on single-cell molecular data. And I'm going to tell you about how we're using machine learning to try to link molecular states with phenotypes. So basic biology, all cells within a particular human share the same genotype with the same DNA sequence, but vary widely in phenotype. So if you think about all the different types of cells in the human body, clearly skin cells and brain cells are very different from bone cells and blood cells. And so a fundamental question in biomedical science is, what are all the cell types and cell states that exist in the human body? And how do their molecular features relate to important phenotypes? And these questions are fundamental to understanding both how the human body works and also how it responds to various perturbations and stimuli and how it goes wrong in disease. So the type of data that I look at in my research is single cell omic measurements. And this type of data is pretty new. And there have been a bunch of experimental innovations that allow people to now measure molecular profiles such as gene expression or epigenetic state in thousands to millions of single cells. And I won't go into a lot of the experimental details, but the basic idea is that you need some way to take a tissue which contains cells of potentially many different types and states, break it up into individual cells, and then load each cell into its own microfluidic droplet so that you can perform a chemical reaction on each individual cell, ultimately linking its molecular profile back to just that one cell. So this type of data, although very useful for giving us the single cell resolution that previous experiments haven't, one limitation is that it doesn't usually give you a label. And so in general, all you know about one of these cells is its molecular profile. And this data comes in the form of a lot of DNA sequences, which can then be processed computationally into ultimately a cell by genes count matrix that tells you, for example, how many transcript copies of gene I are present in cell J. And so sort of the starting point of a lot of research on single cell data is using unsupervised learning to try to discover patterns in the data through dimensionality reduction or clustering. And a big question is, how do these dimensions from dimensionality reduction or clusters relate to these phenotypic properties that we're ultimately interested in studying to understand how the human body works and how it goes wrong in disease? So several examples of some of the things you can get from these unsupervised analyses of single cell data are mapping healthy cell types. Because the technologies are so new, people are still undertaking these large projects to try to map all of the healthy cell types and states in the human body. And for example, there was a recent discovery that there's a completely new cell type in the lung that hadn't been characterized before called the ionocyte. And it turns out that it's that cell type that causes cystic fibrosis. So another application is understanding the differences between diseased and healthy cells, and also understanding the sequential processes of molecular change by which one cell type differentiates into another. And one key challenge with these data types, in addition to the lack of labels, is that you generally can't measure more than one modality per cell. So even though a number of properties like the morphology of the cell, its spatial position, its gene expression, and its epigenome are all important for understanding the cell types and their phenotypes, you generally can only measure one type of thing at a time per cell. So the first project that I'll tell you about is using non-negative matrix factorization to link these different types of molecular cell states. And so we've developed an approach that uses a modified form of NMF, where given multiple different kinds of molecular data, so say for example, single cell gene expression, single cell methylation, and single cell attack-seq, we can use NMF on a common set of gene level features across data sets to jointly factorize the data sets using both shared and data set specific metagenes. And these metagenes tell you both what's the common source of variation across these different modalities, as well as how each of the layers differs. And then the cell factors H allow us to jointly cluster and link these different modalities across data sets. And more recently, I've taken this INMF algorithm and developed an online learning version of the algorithm, which provides several significant advantages. In particular, it allows us to perform this factorization in an online fashion using small mini batches instead of using the entire data set at once. And this allows us to use data sets that are too large to be stored in memory. And we can also even stream data that's stored on a remote server rather than downloading it to the local disk or loading it in memory. And the key quantitative mathematical innovation here is using a surrogate function that asymptotically converges to the same objective value as the batch version of the algorithm. And then that allows us to perform mini batch learning. And there are kind of three different scenarios, depending on the type of data sets that you have, where this is useful. The first scenario is where you have a large but fully observed data set that's too big to fit in memory. And in this case, breaking the data into mini batches allows you to efficiently process the data without loading the entire thing in memory. Scenario two is where you have continually arriving data. For example, I'm part of a big consortium with the Brain Initiative where people are continually generating new single cell data sets. And rather than having to recompute these dimensionality reduction analyses and cluster analyses every time new data arrives, this mini batch update allows us to just plug the new data directly into the solution. And then a third scenario is where you have a large reference data set that's been curated and analyzed carefully, and you have a small query data set that you want to project into that data set. And our approach allows us to handle all three of these scenarios. And as an example of how you can use this practically in biomedical research, we applied this algorithm in scenario one to a large data set of more than 400,000 single cells, including RNA, chromatin accessibility, and methylation. And we were able to jointly embed the modalities, and all three aligned very well. And we were able to identify a corresponding set of about 46 neuronal cell types, which is the most detailed profiling of a brain region ever. So now in the last couple minutes, I'm just going to tell you briefly about some ongoing work. We are using our online algorithm as part of a project with the Brain Initiative. And the consortium is generating single cell RNA-seq, attack-seq, and methylation profiling from every region of the mouse brain, with the ultimate goal of identifying all of the cell types of the healthy mouse. And then once we're done with the mouse, we're going to move on to the human. And so this project, my part of the project, aims to link the molecular profiles of these cells with their anatomical features. And this is really important because in order to understand how neurons function in circuits and ultimately in behaviors, we need to understand how their molecular profiles, such as the markers of these 46 types that I just mentioned, how those molecular profiles relate to the phenotypic properties of the cells. And so the key property that we're going to use to link molecular and anatomical features is spatial position. And we can use the metagene factors that we learn from jointly factorizing these data sets to map the cell types in space. And once we know the spatial distribution of each cell type within a common coordinate framework, we can immediately identify how those molecularly defined cell types relate to other anatomical annotations such as axonal projection data, or even other things like neuron activity during a behavior. And so just as a quick example of what this looks like, on the left, I'm showing a UMAP embedding of the single cell molecular profiles from the motor cortex analysis that I showed previously. And if we look in particular at two subtypes, the L23IT and the L5IT neurons, we can map those back to their spatial position in the coordinate framework representation of the motor cortex. And if we do that, we see that these cell types have very different spatial positions, where L23 neurons are in a layer that's spatially above the L5 neurons. And then ultimately, as I mentioned, putting the cell types in space allows us to link with other types of anatomical data, such as neuronal projection. And we can understand how different brain regions communicate through axon projections. And then lastly, I'll just tell you briefly about a new project that we have going on, which is to predict the effects of perturbations on cell state. There are a couple of experimental technologies that allow you to perform multiplex screening of either drug, treatment, or genetic perturbation and read out the effects of these perturbations on gene expression. And so the problem that we're working on is to be able to predict, given a perturbation, how that perturbation shifts the normal distribution of cell states. And so you can imagine, for example, certain perturbations will shift cells away from a particular mode corresponding to, for example, a healthy cell state. And so my student has developed an approach that blends variational autoencoders and generative adversarial networks to be able to sample from disentangled representations. And we can use this approach to predict drug treatment effects on unseen drug and cell state combinations. And so, for example, if we look at these three drugs shown here, our approach can predict the green cells, and you can see that the green cells overlap with the blue cells, which are the true held out drug and cell type combinations. And with that, I'll end, and I'll be happy to take questions during the panel discussion. Thank you.
Great. Thank you so much, Josh. Alberto, if you could project, you're up next.
Yeah, can you guys see the slides?
Yes.
Okay. So hello everyone, and thank you for the opportunity to present in this workshop. My name is Alberto Romagnoni, and I work in the translational research team at Owkin. So today I will talk about H2RNA. So in this project, we try to connect two words. So all slide images on one side, and molecular data, and more specifically transcriptomic data on the other. Today, pathology imaging is one of the most common and inexpensive tools used in oncology, since they provide a high-resolution map of the tumor that helps pathologists determine diagnosis and grade. On the other side, massive changes in gene expressions are known to occur in many cancers due to mutations or epigenetic modifications. And the characterization of disease-related gene signatures can help to clarify disease mechanisms and prioritize targets for novel therapeutic approaches. All transcriptome sequencing techniques, together with dedicated bioinformatics tools, have been developed. But despite their sustained decrease in cost, these technologies are not routinely used by all medical centers. That's because they are time-consuming and present several challenges impairing their adoption into clinical practice. Therefore, being able to predict gene expression from all slide images, or in other words, augmenting the data images with transcriptomic data, would greatly facilitate patient diagnosis. That's why we developed HA2RNA. So in collaboration with the team of Professor Calderaro from Henri Mondor Hospital in Paris, we designed HA2RNA to be able to predict RNA-seq profiles from all slide images without annotations. By construction, as we will see in a moment, the model can specialize this information on the slide, even if the only information available for each slide and each gene is at the global level. And this work has recently been peer-reviewed and published on Nature Communications. Just a few words about the model architectures and the training and design of HA2RNA. It's a deep learning model based on a multitask, weakly supervised approach. During the learning process, the whole slide image is divided in little pieces or tiles. For each one of these tiles, 256 features are extracted using a ResNet50, pre-trained on ImageNet. The new part of the algorithm starts from these features. For a given sample, and for each tile, and for each gene, a score is assigned by a deep neural network. These scores are then combined in order to provide a single prediction at the whole slide images level. So by construction, as said, the model learns to assign a score to each tile gene combination. This provides the whole slide image with a local transcriptomic representation. In a sense, this enriches the image, which already contains information about morphological patterns, with molecular information contained in the RNA-seq expressions. This transcriptomic representation allows then a multiplicity of applications. The obvious one is that HA2RNA is able to predict RNA-seq profiles without associated RNA sequencing or expert annotations. And in particular, it performs very well on immunology-related genes. The second, less obvious, is that since for a given slide in a given gene, now we have a score at tile level, this automatically can be translated into a neat map of local gene expression prediction. The third enters in a more general framework of transfer learning. The internal representation that the model has of an image, which is supposed to be enriched with molecular information, once the model is trained to predict gene expression, can be transferred to another dataset and used to improve the performance on completely unrelated tasks. So let me mention just a few details of the results. We used matched WSI and RNA-seq profiles from TCGA data on 28 different cancer types. We assessed the correlation with the ground truth for each gene, separately for each different type of cancer. Then we applied corrections to account for multiple hypothesis testing. An average of almost 4,000 genes, including almost 3,000 protein coding per cancer type, were predicted with a statistically significant correlation under the stringent OMSI-DAC correction. Among other things, we investigated whether non-gene signatures dysregulated in majority of cancer types could be accurately predicted by HA2RNA. In particular, we focused on the hallmark of cancers, so increased angiogenesis, increased hypoxia, the regulation of DNA repair system, increased cell cycle activity, immune response mediated by B cells and by T cells. In order to do that, we combined several lists of genes from gene set enrichment analysis software for each of these biological networks in order to obtain 6 lists of genes involved in this pathway known to be dysregulated in several cancer types. And we found that the majority of cancer signatures for these hallmarks were significantly better predicted by HA2RNA, better than random list of genes. So as said, HA2RNA assigns a score to all tiles, so contributing to gene prediction, and is therefore interpretable by design, providing a virtual specialization map covering the entire WSI. So we try to validate the accuracy of such virtual specialization on different datasets. So in the first one, we applied a model trained to predict the expression level of MKA67 to an independent dataset of more than 300 slides of liver hepatocellular carcinoma from the hospital Henri Mondor. So this gene is a well-known marker for cell proliferation, and it's expressed both by tumor and non-tumor cells, clinically determined by immunochemistry staining of WSIs. Its overexpression has been found to correlate with tumor growth, and therefore with fast progression in poor prognosis. So per-tile-like notation of tumors versus healthy tissue was performed by pathologists. We specialized it with H2RNA and compared it with the pathologist annotation. We observed that the tiles with higher expression of MKI67 were almost always located in tumoral regions. In another experiment, we considered genes characteristic of the epithelium in prostate adenocarcinoma. This PESO dataset contains almost, I think, 62 H&E slides with the corresponding segmentation masks generated by using a multiple staining procedure. We trained a model predicting the 3 corresponding genes on TCGA prostate adenocarcinoma and applied it on this dataset. And we compared the average predicted expression of these 3 genes at the level of the individual tiles. And we compared it to the fraction of epithelium given by the segmentation mask, and we found a significant correlation once again. And finally, we studied the prediction of immune responses related to gene expression. As a majority of tumor-infiltrating lymphocytes are known to be T and B lymphocytes, we consider a subset of genes specifically expressed by each cell type. In particular, to define the T cells, we consider the CD3 genes, while for the B cell population, we consider the CD19 and CD20. So we validated the specialization of the T and B cells model, learned on TCGA data on an external H&D CD3 and CD20 double stain slides from always from Henry Mondor Hospital. We calculated the correlation between the expression per tiles predicted by this H&E staining and the actual number of T and B cells that we obtained by using a QPath software on EHC stained images. And once again, the model has shown good results. So the third application of H2RNA enters in the general framework of transfer learning. To illustrate one possible clinical application, we studied the prediction of microsatellite instability status, or MSI status. The microsatellite instability is a phenomenon due to the failure of mismatch repair to correct the replication errors at tandem repeats of short DNA sequences, known as microsatellites. MSI status was recently identified as a predictor of the efficacy of anti-PD-1 and anti-PD-L1 immunotherapy. Recent studies, and in particular in a seminal paper of Cater and collaborators, already showed that convolutional neural network can learn to predict MSI status directly from WSI. So based on these results, we collected the TCGA colorectal cancer datasets and trained H2RNA. We then considered a setup in which this dataset was randomly split between 2 different hospitals. In Hospital A, only WSI and RNA-seq are available. And this first subset of WSI is used to train an H2RNA model to generically predict RNA-seq data. In Hospital B, a second subset of WSI and MSI status are available. Also, the trained HRNA model from Hospital A is available, but only the model. In this scenario, a medical researcher of Hospital B wants to predict MSI status from WSI images, and has 2 options. So, or train a model to predict MSI status directly from images, or train a model to predict MSI status from the internal transcriptomic representation that he obtains by applying the H2RNA model trained on Hospital A to these new slides. To test H2RNA robustness, we consider several different splitting of this CGA data between the 2 hospitals of this scenario, and different splitting proportion for the data subset used in the 2 hospitals. What we observed is that in this situation, in the situation where the researcher of Hospital B has access to less slides than Hospital A, then transfer learning classifier based on the H2RNA outperformed a classifier trained directly from images. So in this way, showing the importance of the transcriptomic representation. To sum up, one can imagine a variety of questions and problems that can be addressed with H2RNA. Genomic data augmentation by adding, for example, RNA-seq data to existing cohorts of non-sequenced patients. Or one can identify well-predicted genes and create new signatures for specific endpoints and provide new biomarkers. Biomarkers that can be revealed also by visually identifying new morphological patterns related to specific mutations by using the local visual specialization. Moreover, we can also imagine to push that forward and improve the slide analysis with a sort of virtual staining and ideally replace immunostaining. Finally, we can use the transcriptomic representation learned on a cohort by transferring the pre-trained model on smaller cohorts and build a better model for the prediction of specific targets like HRD or MSI status. So let me finish by acknowledging all the colleagues that participated in this project, and in particular Benoit and Elodie, which did most of the work, and Professor Julien Calderaro and his group for realizing the experiments and providing the external validation data, and more generally for the assistance on the pathology pattern interpretation. Okay, thanks.
Great, thank you so much, Alberto, for that good talk. Our final speaker is Johan. So if you could project, thank you.
Yeah. And are you able to see my slides okay?
Yes.
Yeah, okay, great. Okay, so first of all, thanks to Jing and Patrick for organizing this workshop and for inviting me to participate. And I know one of the goals of this workshop is for us to be able to introduce ourselves to one another. I'm an assistant professor in the statistics department here at the University of Michigan. And broadly, my research falls into a few broad areas. I work on problems in genomics. I also work on problems in causal inference. And in both of these, I have a strong focus on applications. And so my original plan for this talk was to talk briefly about a little bit from each of these. And in particular, in genomics, I was going to talk about some work that I'm doing accounting for and making sense of latent variables in genomics, in genomic data, and in particular in the context of high dimensional classification. For causal inference, a project that I'm working on right now that I'm pretty excited about has to do with combining observational and experimental data. And in particular, the goal of this project is to use large observational data sets to improve the precision of small randomized trials. And in particular, with a focus on making sure that no biases in the observational data in any way leak into the final results in the randomized trial. And then I was going to talk about this all in the context of some applied work that I'm doing involving large cancer drug screening studies. Given the time constraints, though, I eventually decided that I'm just going to focus on this one, looking at the role of latent variables in high dimensional classification. But I'm still going, and so all of this is in some way a bit of an apology that despite the title of the talk, there's not going to be a whole lot about large-scale drug screening studies in this. But I still will use that to motivate the rest of the talk. And so that'll be the next slide. So what are large drug screening studies? Well, on the one hand, these are studies where essentially the ultimate goal is to try to figure out predictive biomarkers for when certain drugs will be effective on different types of cancer. And so in these large screening studies, you'll have, on the one hand, cancer cell samples. And in the studies that I've been looking at, there are thousands of samples, and these are typically cell lines. And then you also have a whole bunch of different possible drugs. Some of these are drugs that might already be in use. Others are ones that are potential drugs. And in the studies that I've been looking at, typically there are hundreds of drugs. And then what will happen is that there will be a large, all possible combinations will be assayed. So each of the drugs will be assayed against each of the samples, each of the cancer samples, and then you'll have efficacy data on all of these combinations. And then at the same time, you'll have a bunch of genomic data on all of the cancer samples. So gene expression data, methylation data, genotype, copy number, these sorts of things. And then the goal is to be able to use this genomic data to predict which drugs will be effective against which cancer samples. And so there's obviously various benefits to this. There's biological understanding, learning more about the mechanisms of how different compounds are effective against different cancers. There's the goal of personalized treatment, being able to figure out for individual patients which drug might be most effective. And so those are probably the most obvious, but then there's other reasons to do all of this. And just one other example would be using these databases to inform clinical trials. So for example, if you're able to predict which drugs might be effective against which cancer subtypes, that might help you improve eligibility criteria when you're designing a randomized trial. It can also help you improve the precision of the final trial results, and especially might help be able to improve the precision of specific subgroup analyses. Okay, so that's some general background on drug screening studies. The two of the main studies that I'm looking at are CCLE and the genomics of drug sensitivity in cancer. Okay, but I'm going to move on now and start talking a little bit more about specifically some issues related to latent variables and prediction. And to set this up, I want to consider just a toy example. And so imagine that we are trying to predict using some sort of, let's say, gene expression data to predict or to classify two different types of lung cancer. We'll call them type A and type B. And let's just say that type A, a certain drug is effective, and in type B, this drug is ineffective. And just again, hypothetical, I want to imagine for a second that the difference between type A and type B is just due to a single gene. So in this hypothetical example, let's say that whether or not this drug is effective or not is going to entirely depend on whether a certain gene is dysregulated or not. Okay, so obviously, we want to, when we build our classifier, we want to have some focus on this gene. But of course, that signal, the difference between type A and type B, that's certainly not the only signal that exists in this expression data. And you can imagine that there's plenty of other signals that are floating around as well, such as age, smoking status. Now, again, for cell lines, this might not be quite exactly the best examples to be thinking of, but if you imagine, for example, a tissue taken from directly from a person, the age of the person, whether or not they smoke, also things just like where they are in their circadian rhythm when you extract the sample, whether or not they just ate, and then of course things like technical batch effects as well. And a lot of these other signals in the data affect many genes. So things like smoking status, for example, has been shown to affect the methylation pattern across a very wide number of genes. And what I want to think about in particular is what if some of these other signals happen to be correlated with the different types. So again, in this hypothetical example, we're imagining that whether or not it's type A or type B is due entirely to just one gene, but that doesn't mean that some of these other variables might still be correlated with type. So for example, it might be that people who smoke are more likely to end up with type A than type B. And so even though there's not a direct causal relation, it might be that still smoking status is predictive of whether you're type A or type B. And so these variables, all of these other variables that are kind of ever present in genomic data, these present both challenges and opportunities in the context of prediction. Challenges because in some sense they add additional noise to your data, but also opportunities because, again, if you think about the smoking status example, they might also add some predictive value. Okay, so this general issue we explore in a paper that we recently posted. This is joint work with a graduate student of mine, UG Japan. And the rest of the talk is going to be a very brief, high-level overview of this paper. So start off by considering just a really simple model for let's say gene expression data. And S, we can think of S as our gene expressions. We've got N observations, so N tissue samples, P features, P genes, and we're going to think of this as essentially just a function of the class indicator, so type A or type B, and then the effect, and this, importantly, this is like the direct effect of the class indicator plus some epsilon. And in this model, there's no latent variables. And going back to the example with lung cancer, imagine that this gamma is very sparse and that in fact, there's only one entry in there that's not null. And so that's gonna be the entry that really, the one gene where if it's dysregulated, you're type A and otherwise type B. Okay. Okay, so that is a very simple situation where there are no latent variables. And in this very simple setting, the Bayes optimal classifier is also itself very simple. It's essentially a problem for diagonal linear discriminant analysis. You've got this linear classifier, and importantly, this optimal weight vector is sparse. And in fact, only one entry of it is going to be non-zero. So now let's say that we throw in some latent variables. And so I'm going to take this same model, and I'm going to add this term here for latent variables, things like age and smoking status and stuff like that. We'll say that there's K of them, and we can think of this as just the simple model that we had in the last slide, but now we're tacking on these latent variables. Okay, so I'm going to continue to reserve S here for this simple part, which is just the T gamma plus epsilon, and then the L alpha is going to be the latent variable term. And so now Z is actually going to be the gene expression that we actually observe. This is going to be the observed gene expression data. Neither S nor L nor alpha are directly observed. Okay. In this case, the Bayes optimal classifier, it's still a linear classifier, essentially something that you would get from an LDA. But a critical point to make is that the weight vector is no longer sparse. And that's even if the latent variables are uncorrelated, are not predictive, and even if the gamma itself has only one non-null feature. Okay. Okay. That's something that's not too deep if you look at the math, but I think it's also something that tends to get forgotten about a little bit in applications. Okay, and then I'm already starting to run out of time, so I'm going to go just a little bit faster. But the basic strategy of our approach is that we're going to try to find a way to recover S, because then the classification gets a whole lot simpler, and we can use very simple techniques such as diagonal LDA. This slide makes the point that if the latent variables are correlated with your phenotype of interest, then L itself is predictive. And in that case, we don't want to recover only S, but we need to recover both S and L. Okay. And so just very briefly, conceptually, our approach is this. We start with our gene expression data. We infer the latent variables using, for example, singular value decomposition. We then residualize to get the direct effects. So to remove the latent variables, we build classifiers on both the latent variables and the sparse component separately, do an ensemble, and get our final predictions that way. Again, just skipping over things pretty quickly. In practice, we've got some nice ways of going about this where we actually don't even need to compute a SVD explicitly. We don't even have an explicit estimate of L. And as a result, we don't need to worry about any tuning parameters. And as a result of that, it's very fast. One other thing to point out is that getting this S part for the training data, or excuse me, for the test data is particularly tricky. Here's some simulations. I'll skip over them. Here is some real data. I'll just put that up very briefly. The basic point is that it works pretty well on a bunch of different types of data, different types of genomic data, different platforms. And I'll leave it at that. Thank you very much.
Great. Thank you so much, Johan, for that great talk. All right. Thank you, everyone. It is time for the panel session for session number 2. And before I begin that, I just want to thank again everyone who participated, Ambuj, Camille, Barzan, and Mathieu for session 1, and all the presenters from session 2. So once again, there's a Q&A box at the bottom, and audience members could just input questions as they come. So I think a first general question, which touches on all of your talks, and just a quick reminder for the audience, in this session, we covered calculating COVID-19 severity scores with Simon, identifying cellular states using single cell techniques with Josh, predicting transcriptional signatures from histology slides with Alberto, and determining the effects of latent variables from Johan. So a general question is, what do you think the challenges and the limitations are to applying such predictive models for clinicians and scientists who don't have machine learning backgrounds, who don't understand all the nitty-gritty of all these things? What do you think the biggest challenges for interpretation of these models would be? And I think I'll just pull everyone in as a roundtable. So I guess I'll start with Simon, and I'll just go down the list.
Yeah, so if we take the example of the models for COVID-19, the thing is that I think if you want to go to the clinic, you need first to generate trust into your model. And that goes first through large validations of the model. But even if you have a strong performance, and I think as a data scientist, we have a strong bias into looking at just often the metrics of our models. I think there are at least two things to consider, which is, can you give more interpretability to your models? So if it's just a simple logistic or linear regression, maybe just on how you present the results to the practitioner. For deep neural networks, I think it's much more tough questions, especially maybe not when it's algorithm for, let's say, segmentation. For instance, I don't think we really need to explain how it works when your algorithm is just here to segment lesions on the CT scans or on the histopathology images. But when it goes to a diagnosis tool, here you need to provide much more details on how, what are the internal mechanics. So for instance, for the paper on COVID-19, we showed that the internal representations of the neural network correlates very well, for instance, with the disease extent or some clinical variables. And then there are a bunch of techniques I think people know on how to interpret neural networks. Mm-hmm. And the second point is really how do you integrate your solution into the workflow of the different clinicians, and what do they need to see regarding your algorithm to trust it and use it.
Thank you. Josh, do you have any inputs?
Yeah, I think one unique challenge with the type of data we look at is how little humans actually understand gene expression profiles. So just as an example, when my student was developing this new GAN plus VAE approach for single cell data, we were trying to assess disentanglement performance and generation quality. And for image data, there are well-established ways of doing this, and we can sort of have confidence in the metrics that people develop because our brains are really good at looking at images and understanding whether they look realistic or not. But we don't have the same capability with genomic data. So compounding that is that we don't really have ground truth labels for a lot of these data types. So it's very challenging. And I think that's why a lot of the focus now is on sort of like unsupervised pattern discovery, because we're trying to build our knowledge of these data types.
Mm-hmm. Thank you. Alberto?
Yeah, so I completely agree with my two colleagues. There are different challenges depending on the different data type and also different application. In particular, I completely agree about the difficulties in interpreting what is a genomic expression is very complicated with respect to the images. So the advantage, for example, of the kind of model that we developed is that naturally by construction, you can give an interpretation of importance in the prediction coming from the different part of the images for a given gene, for example. And then you can compare it with you can interact with the pathologist and see what is their interpretation of this particular part of the images, and then improve the model or convince yourself that that's the good way to go. So yeah, that's my 2 cents.
Great, thank you. And Johan?
Yeah, I'll mention 2 things. One is it can be sometimes hard to communicate just the level of heterogeneity that is out there in real applications. And as I say that, I've got in mind a project that I'm working on right now that's actually very similar to Simon's, working on a COVID-19 risk score. And we also have a very simple, reasonably interpretable model. And in fact, our strategy was very, very similar to Simon's in a lot of ways. But even with like just a few variables in the model that are very highly interpretable, it's still the case that it gives fairly different results at different hospitals, simply because, you know, one hospital might have been swamped with patients, whereas another one had very few, and everybody got really good care. Mm-hmm. And so when you go to talk to clinicians, you know, they might want to know, like, if someone comes in with this pulse ox and with this and with that, what's their chance of surviving? But it depends on very much just on the hospital that they're at also. So it can be hard to give a clear answer to that. So yeah, the level of heterogeneity that's out there is something. Another would be, and this is related to what Josh and Alberto just said, is interpretability of, especially for example, genomic data. So I gave this example of where the classifier might do better if it implicitly took into account smoking status, because that is correlated with the type. Now, whether or not you want the classifier to do that is a legitimate question. It might be that you already know someone's smoking status. It might be giving you information that you already know. It also just might not be what you want to know for various reasons. And if you have just kind of a black box prediction algorithm, it will take into account smoking status if it's in there, whether you want it to or not. And part of the reason that we developed this method that I just talked about, one of the original inspirations for it was actually like to be able to get additional interpretability by being able to explore separately what are these latent variables that are showing up and what are the genes that seem to have a direct impact beyond those latent variables. Yeah, basically just like, again, just reiterating this thought that sometimes things are, the predictions that you're getting might be based off of things that you already know or not what you're actually most interested in.
Thank you for that. So we have one audience question. It's about labels in biomedical applications that are difficult to obtain because you need expert opinions on this. So how much are we focusing on unsupervised approaches, and where do you think we are on this front? I saw that Owkin uses a lot of supervised learning. So maybe Alberto or Simon, I can pass this to you as you worked on both histology and CT scans.
Yes, so you're totally right that it's much harder to get big annotated data sets in biomedical applications. I think in computer vision, last year maybe has been the year of self-supervised learning, where we've seen methods on unsupervised learning well for the first time. And so we've been working on these methods. And for instance, in the model we developed for the COVID-19, we used unsupervised learning. So mostly we use the MOCO approach. So I can send you a link in the chat after. And we've been using that for histology also. And it's working really well. I think we've been first explored for a few years transfer learning. So how you can leverage big external data set and then transfer the neural network to your new data set with a few labels. But I feel now that these new techniques with self-supervised learning based on contrastive losses can be really game changer in many applications.
Great, thank you.
I don't have to add much to that since Simon already said about the histology. Just a comment that even a weekly label is, I mean, even if we don't have labels for each part of the slides, sometimes if you use a huge number of slides, then you can infer at least some local information. But yeah, mostly what Simon said.
Thanks. And if Josh or Johan, you have any inputs? No? Okay, so there's another question in the Q&A. When transfer learning is used by representation, as in histopathology use case, is it possible to use the representation model to calculate the original data? Do you think this is an obstacle for usage of federated learning, and are there any methods you could use to prevent this? So Alberto, they mentioned histopathology. I will swing this question to you.
Yes, I have to think about it. I don't know how much information one can recover for that. Well, the original data, you mean from the from the weight of the trained model. well, I don't know if Mathieu is here, so maybe he has a more insightful opinion, but I don't have an answer to that. But that's maybe an issue indeed.
Okay.
Also, I think the method of self-supervised learning are really well suited to federated learning. In fact, like you don't need labels, and it's easier because you don't face this problem of heterogeneity of the labels. For instance, if you just want to learn a representation from the images from the different centers, so I think it's quite interesting to use federated learning to train unsupervised algorithms.
Mm-hmm. Great, thank you. So one more audience question. For genomic data, is to get a sense of the normal or ground truth, what did the panelists think about applying normalization flow method to this problem? How about we start with Josh or Johan?
I think normalizing flows can be a useful tool, but I'm not sure I see the connection with the way the question was asked in terms of ground truth. But yeah, certainly, particularly for the kinds of generation tasks that I was talking about at the end, GANs, VAEs, and normalizing flows are some of the big players in terms of high-dimensional data generation.
Okay, thank you. So we have a couple minutes left. I'm just going to throw out one broad question, and whoever wants to take it, be interested to hear your insights. So I wanted to ask about the challenges of incorporating multiple types of modalities and data sets for model refinement. Obviously, the higher number of data or the different types of data that you incorporate, whether it be like gene expression, RNA-seq, ATAC-seq, enhancer data, copy number, et cetera, the prediction score or the model will always become greater and greater of higher resolution. But when is enough? Like, when is the model good enough where refinement won't add much more to it? I'll just throw this out to all the panelists. If anyone wants to take it, Johan or Josh? Or Alberto or Simon?
Yeah, I can say something. So I would say that first of all, it's not so obvious that adding new information you will improve your performance. And I think that the answer is it depends. It depends from what you want to do. So if you want to have insights in the interpretability, or you want to connect things, connect dots, and have a more let's say complete image of what is happening at the biological level, then adding new modalities can be helpful. But again, adding data can add noise. So yeah, I agree that it's a difficult trade-off. It's a difficult trade-off.
Great, thanks, Alberto.
I'll say that just from my own experience, and this is pretty generally speaking, that there ends up being a trade-off with generalizability, and I'm not just talking about like overfitting in the purely statistical sense, but the more complicated you make a model, even if it is like legitimately a good model for the specific scenario that you're looking at, again, thinking about heterogeneity of, like, for example, different hospitals or something like that, you just generally run into a wall where making it more complicated also makes it less generalizable. So that's kind of how I think about that trade-off.
Yeah. Josh?
Yeah, just one more thought. The more data types you have, the more expertise you need in terms of understanding the unique issues of each data type. So, for example, people who are experts in computer vision know very well how to pre-process and images and how to filter out bad images. But if you start to try to apply the same models to genomic data, there's a completely different set of issues, and it requires some significant expertise to understand, the unique issues of data. But then when you put those two together, there's even more special, issues that you have to consider in terms of balancing the two data types and what each unique type brings. So I think that the more data types you have, the more understanding of each type of data is required.
Yep, I absolutely agree. Thanks, Josh, for the answer. So we're coming up to the end of the session. Just wanted to thank again Johan, Alberto, Josh, and Simon, and the speakers from the first session. I think Jing Liu wants to give a closing statement. And thank you all again. And we are excited to partner up with University of Michigan. Go ahead, Jing.
Yeah, so I want to make sure I thank two staff members who put in a lot of effort to make this workshop happen. That's Talia Lateras from Owkin and James Walsh from MIDAS. And also thank you all for the speakers, moderators, and the audience members. If you want to continue discussing with the team, go online, find MIDAS or Owkin websites, find our emails, and get in touch. With that, thank you, everyone. Have the good rest of the day. Bye, everyone.